Excellent. All right. So section 7.3, what we're going to do, since we've been learning about radicals, everything we've talked about with radicals so far has been like a square root or a cube root of a number that we get a nice whole number answer. For instance, we've done the square root of 100 or the square root of 81. But the question then is, what happens if the number under the radical doesn't have a nice whole number or a nice integer times itself a certain number of times? So what we're going to do is we're going to take advantage of the what's called the product rule of radicals. This is going to be the big thing for the next 3 sections, dealing with how to simplify radicals. Again, another skill that we go through in this class, that when you get to college algebra, if that's your math destiny, if that's what you're taking next semester, you're going to use this a whole lot. Okay, and I'm not gonna have time to go back through it. I'm just going to assume you've got it. So what the product rule of radicals says is this: is if you've got the nth root of A and the nth root of B. So one thing to notice right away is that the index is the same. Product rule of radicals does not apply if you have different indices. You would have to do something completely different, and we may or may not have time to go over that situation. So if you've got the nth root of A and the nth root of B, they're real numbers, and n is a natural number. So the index is a natural number. Again, in this class, we're not going to go through any situations where n is something else. That's all sorts of fun happens. Then the following is true. If you have the nth root of A times the nth root of B, since the indices are the same, then what you can do is you can put the whole multiplication under its own radical. And this can go both ways. If you have stuff under the radical, you can separate it if you need to, or you can multiply it. We're going to go through both situations. So for instance, just the next bunch of problems is just getting used to this new thing, the product rule of radicals. So my example right here, example 1, is if I have the 5th root of 5 times the 5th root of 7, notice the index on both of these radicals is 2. And so since that is the case, I can go ahead and multiply the stuff under the radicals, and I get the square root of 5 times 7, or 35. Nothing else I can do with that problem. It's just a straight, let's get used to using the product rule of radicals. All right, so yours, exercise 1, right next door. I'm going to give you 15 seconds. Write down what you think is going on in exercise 1. All right, exercise 1, I've got the square root of 7. I've times the square root of 11. So what's going to be my result here? Perfect. Excellent. Well done. You have caught on to the product rule of radicals. Since the indexes are the same, that becomes the square root of 77. Fantastic. All right, exercise 2. The purpose of exercise 2 is just to familiarize ourselves with the idea of, if stuff is outside the radical, I can multiply those things times each other. And then if stuff's under the radical, I can multiply those things times each other. So go ahead and give exercise 2 a try. See what you come up with. All right, when I multiply these two things together, what's the number outside the radical going to be? Yeah, we've got a 2, we've got a 6. You multiply that in the usual way, you get 12. And then I'm going to have what after the 12? Square root of, you probably implied that, but the square root of 15. Yes, for sure. Now notice, here's the thing. That radical, remember, the radical is an operator. It's telling you to do something. So I cannot say 12 times 15 is whatever that is. Okay, the radical is like a force field. Okay, you can't just go through the force field until you do the thing the radical is telling you to do. Okay, exercise 3. It's just going to have you do the product rule of radicals with variables. Just trying to hit all the different situations as we learn this new concept. All right, so this one, we got the square root of 2x times the square root of 5y. What's the result going to be? Square root of 10xy. Fantastic. Just two more. Same thing on both of them. So we're doing one at a time. Exercise 4. The only difference with exercise 4 is I've changed the index from a 2 to a 3, just so that we don't get into a rut. So I've got the cube root of 4 times the cube root of 5. That turns out to be what? Cube root of 20. Yep. The index on both those radicals is the same, so I am allowed to use the product rule. Perfect. One more, exercise 5, same sort of thing. All right, and so again, nothing really different here. My index is the same on both radicals, so this is going to be the fourth root. And then under the radical, I've got 5 times 6 is 30. Remember, I default to alphabetical order. If you have the variables in a different order than me, that's fine, but I'm going to do t times x to the third. So if you've got x to the third times t, that is fine. The order doesn't matter. All right, so that's the product rule of radicals. We doing okay so far? All right, well, we're going to come back to that in a second because that's going to be super useful for us as we deal with radicals, but there's another property of radicals that I'm going to mention. In fact, we've already kind of used this and assumed it when we first started talking about radicals. This is the quotient rule for radicals. Remember, quotient means division, means fraction. And so what it says is this, is if I have the nth root of a and the nth root of b, again, the index is the same on both of these. If both those are real numbers and n is a natural number, again, I'm never going to make that any different. The following is true. If you have the nth root of a fraction, then what you can do is you can break it apart and do the nth root of the top and the nth root of the bottom, and vice versa. Okay, and again, we did this, if you remember the first day we started talking about radicals, I think one of the problems I gave you was, let's find the square root of 9 over 4. And I told you at that time, when you have a fraction under the radical, you can just do top and bottom. That was using the quotient rule of radicals. So for instance, my example 2, says, let's find the square root of 7 over 36. Well, here's what I can do, because I know 7 doesn't have a nice, perfect whole number square root for me. So what I'm going to do first is I'm going to break this apart into the square root of 7 over the square root of 36. Now, in this particular situation, 7 does have a square root, but it's an irrational number, meaning it's a decimal that never ends, it never repeats. You can't write it any simpler. So that's why we'll leave the square root of 7 just that, square root of 7. We can't make that any simpler. But in the denominator, what's the square root of 36? 6. No more radical because we did the operation, so it's just going to be 6 underneath. I can't do anything else with the 7 and the 6 because one is under the radical, one is outside the radical. This is completely done. There's nothing else to do. So please try the same thing on exercise 6, right next door. This is just like something we did when we first started talking about radicals. If you don't even need to write down the quotient rule, I get it, no worries, but I'm just going to be thorough here just for your notes. So this is the square root of 49 in the top. It's the square root of 36 in the bottom. And so in the top, square root of 49, your calculator told you, or you already knew that that's 7 times 7. And then the square root of 36, that's 6. So we have 7/6 as our result. Let's flip the page. There's another quotient rule problem at the top for you to do. Exercise 7. Simplify the square root of 3/144. Right, so quotient rule says that I can break this thing apart. So I've got the square root of 3 in the top. I've got the square root of 144 in the bottom. Square root of 3 can't be simplified anymore. It is just the square root of 3, so I'm going to leave it under the radical. In the denominator, the square root of 144, what is that? 12. Again, I just want to make note of this because I don't want you to overdo it. This 3 is under the radical, the 12 is not, so you cannot cancel the 3 with the 12. Okay, they're not in the same position. One is under the radical, one's not, so this is completely simplified, nothing else to do. All right, one more problem on the quotient rule. Go ahead and do exercise 8 right next door. All right, so this one, the only difference on this problem than the other 4 we've done is this has a 4th root instead of a square root. So I have the 4th root of t in the top. I've got the 4th root of 16 in the bottom. I have no idea what to do with the 4th root of t, so I'm not going to think about it too much. Just going to rewrite it. And then the 4th root of 16, the number that times itself 4 times gives you 16. That is what value? Perfect. Okay, great. So that's the product rule. That's the quotient rule. And we'll come back to the quotient rule later in a different section. We don't really have too much to say about it so far, but the thing that's going to be useful to us for the next couple sections, the rest of this section, and then the next 2 that we do, is we're going to go back to that product rule. So for instance, example 3, this is my example. So for the first time under the radical, I've got a number that I can't ask myself what number times itself gives me 20. There's no nice whole number times itself gives me 20. If you put the square root of 20 in your calculator, you get a long decimal, okay, which is great for doing calculations, but it's not simplified. And so here's what I notice, okay, the square root of 16 equals 4. The square root of 25 equals 5. So what I do know about this value, square root of 20, if I can simplify it all, since 20 is between 16 and 25, then this value, square root of 20, must be between 4 and 5. Well, how can I simplify this? Here's the question that you're going to get used to asking. Notice we've got a whole bunch of problems we're going to do together here. The question that you want to ask yourself is this: is there a perfect square factor of 20? Okay. So whatever number's under there, is there a perfect square factor of 20? Now, in case you don't know what I mean by the perfect squares, I'm going to just show you. I'm going to, on the other side of the page where I've got a little room, I'm just going to write out some of the perfect squares for you. Perfect Squares is my band name if I had any sort of musical talent. Okay, the perfect squares. Okay, so here we go. The perfect squares, what I mean by this is just the following numbers. 2 times 2, that's 4. 4 is a perfect square. It's the same number times itself. 3 times 3, that's 9. 9 is a perfect square. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7, 49. 8 times 8, 64. 9 times 9 is 81. 10 times 10 is 100. I'm getting bored. I'm going to stop here in a second. 11 times 11 is 121. 12 times 12 is 144. And you can keep going forever listing the perfect squares, but you kind of see what's going on. A number times itself gives you a perfect square. So what you want to know, what you want to ask yourself is there a number on this list that is a factor of the number underneath the radical? And so, is there a perfect square factor? Is one of these numbers on this list a factor of 20? Remember, a factor is a number that you can divide evenly into 20. Is there a number here that you can divide into 20 evenly? Yeah, exactly. 4. Okay, so I'm going to write out all the work. The first few you do, you probably need to write it all out, but you'll get to, after you do like 3 or 4 or 5, you'll figure out the shortcuts. I have no problem with using the shortcuts. Okay, so here we go. Square root of 20. I'm just going to break this apart. As I was told, 20 is 4 times 5. In case you're asking yourself the following question, hey, Perkster, why did you pick 4 times 5? Why didn't you pick 2 times 10? The reason is because I needed to have a number off this perfect square list. 2 times 10 is not going to simplify for me. But here's why 4 times 5 is good. I'm going to use the product rule of radicals. Okay, this step right here is what we did on the previous page, just in reverse. I'm now going to give each of these two things their own radical. So I'm going to split it apart. So the square root of 4 times the square root of 5. And if you need to make a note for yourself, how come we did that? That's the product rule of radicals from the previous page. And now here's my final step. And here's the reason that I did that. The first radical, square root of 4. What's the square root of 4? 2. That's why I picked the value 4 as my factor. Okay, the square root of 4 is 2. It's now outside the radical. I've done the operation that the radical tells me. The square root of 5, square root of 5, it's not going to have a nice simple number answer, so I'm just going to leave it square root of 5. And this right here, 2 square root of 5, that is the simplified version of the square root of 20. All right, so we're just going to take a couple problems here, and we're going to get used to doing that because I'm assuming, my assumption, this is a new skill for you. Okay, if you already know how to do this, great. You're just a step ahead, and that is fantastic. Exercise 9, square root of 45. So the first question, is there a number on this list here that divides into 45? And then go with the rest of it. All right, so when you ask yourself the question, is there a number on this list that divides into 45? What'd you find? Yep, 9 times 5. Perfect. It's 9 times 5. And so now I'm going to break that apart. I'm going to give them each their own radical. This is the product rule of radicals that we're basing this whole process on. And now here's the simplified answer. Square root of 9, that becomes 3. No more radical because we did the operation. Square root of 5. No simplified answer, so we leave it square root of 5. There we go. Exercise 10, same sort of thing. Just another example to get used to doing this. What number on the list goes into 50? 25. 50 is 25 times 2. Yep, don't be afraid to use your calculator and mess around with that, figure out what's going on. I'm going to now give these each their own radical. As you get used to this, if you do not need to write this step out, I totally understand. No big deal. Okay. But just make sure when you write your answer, you're writing the proper thing outside the radical and the proper thing under the radical. Square root of 25, we would all say is 5, no more radical because we did the operation. Square root of 2, that's as simplified as that gets, so it's square root of 2. All right, one more. Square root of 700 is the next one. All right, what number on the list goes into 700? Yep, 100 times 7. So again, just to be precise, I'm going to give them each their own radical. And then the square root of 100 is 10. Square root of 7 is as simplified as it gets. Now, I do want to make one note, okay, because this happens sometimes with some of these problems. Somebody in here might have said something like this. So you don't have to write this down. I just want to show you what to do if this ever happens to you. Somebody in here might have been going through the list and said, "Oh, I see that 25 goes into 700." And you might have started out with 25 times, and I don't even know what that is. So 700 divided by 25 is 28. And that's a lovely place to start. But just remember, when you're simplifying something, just make sure you've simplified all the way, because now 28 also has a factor on this list. So you can now go that that's 25 times, and 28 is 4 times 7. So you're going to end up in the same place that I did, but because 700 is a larger number, you might have just not seen the full factor. Okay, so that happens sometimes. Just make sure you simplify all the way to get to your final answer. All right, the next example I've got here, we're doing the same thing, but this time I've got, instead of a square root, a cube root, just to show you that there's no difference in our process. This time, since my index is 3, my question is just a little bit different. I want to know, is there a perfect cube? Now, in case you don't know what the perfect cubes are. Two times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. I'm going to go just one more. 5 times 5 times 5 is 125. And you can keep doing that. Those are the perfect cubes. So it's a different list of numbers. So when the index changes, just make sure you change the list of numbers you're referring to. Is there a number? Is there a perfect cube that is a factor of 24? Yep, you got it. 8. So cube root of 24 is the cube root of 8 times 3. Notice I did not pick 4 times 6 because this is a cube root problem. So now I'm going to give them each their own radical. That's the cube root of 8 times the cube root of 3. And the cube root of 8 is 2. No more radical. We did the operation. And then cube root of 3. All right, try exercise 12. I'm giving you some perfect cubes. You've got your calculator, or you got a calculator on your phone, or wherever you're using it. You can figure out a simplified way to write cube root of 54. All right, when you messed around with your calculator a little bit, what perfect cube divides evenly into 54? 27. Excellent. Well done. So it's the cube root of 27 times 2. Product rule of radicals says that can be written as the cube root of 27, cube root of 2. Cube root of 27 is 3. No more radical. Cube root of 2. All right. We're learning to manage our numbers. Great job. We're going to come back to that. We're going to link that up with the next skill, and then you're going to be just as proficient at the product rule of radicals as you'll ever need to be. Okay, so example 5, my next example. We haven't done a whole lot with variables under our radicals, so we're going to talk about this. So mainly for these problems, I don't go too much into anything but square roots. You might see a cube root problem on the homework, but I don't think so. I think I got rid of those, but one might be hanging around. So answer this question for me. If the square root means the same number times itself, what is the same thing that times itself that gives me x squared? The square root of x squared is what? Yep, x times x. So we're just going to put an x there. Well, let's do this for all of these problems and see if we can figure out the pattern. The square root of x to the 4th. Yep, x squared times x squared. 2 plus 2 gives me 4. How about x to the 6th? What's the square root of that? X cubed. 3 plus 3 gives me 6, so x cubed. One more. Square root of x to the 20th. What times what gives me x to the 20th? Yep, perfection. X to the 10th times x to the 10th. So here, what's the pattern? Math is all about patterns, so we're looking at this. What do we do when we take the square root? What do we do to the exponent each time? Well, yes, you add it to itself. So 10 plus 10 is 20, and 3 plus 3 is 6. But how does 4, what do I do to 4 to get 2, or 6 to get 3, or 20 to get 10? What is the simple, quick way to process this? We're dividing by 2. Yep, you're taking half the exponent, so we divide by 2. So just to see if you followed the pattern, exercise 13, exercise 14, you can go knock both of those out. Okay, we're just taking the square root of those nice even exponents there. All right, so square root of x to the 26th. What is that going to be? Yep, x to the 13th. Great job. Okay, 13 plus 13 is 26. Since we're taking a square root, we just took half that exponent. Great. If I take the square root of x to the 18th times y to the 42nd, that's going to give me x to what power? 9. And then y to what power? 21. Great. All right, well then here is the last new thing that I have for you as far as related to our product rule of radicals. Flipping the page. So now we know what to do when there's an even exponent under there. You take half. So now I've got the square root of x to the 7th. So unfortunately, the simplified result here is not 7 divided by 2 or 3.5. We wouldn't write x to the 3.5 power, unfortunately. Here's what we will do. Anytime you see an exponent under a square root that's odd, here's what you do. I'm going to break this apart. I'm going to use the product rule of radicals. What is the next even number below 7? 6. So what I'm going to do is I'm going to separate x to the 7th into x to the 6th times x. Do I still have 7 x's underneath the radical? Yeah, I got 6 of them are right here. The other one's right here. I just took the odd one out. And so now I'm going to use the product rule of radicals, just like we were in the previous page when we did the square root of 20 or the square root of 54. Okay, and I'm going to say, okay, that's the square root of x to the 6th times the square root of x. And the point that I did, the reason I did this, the reason I picked the next even number below is I'm just taking the square root of x to the 6th, which you just told me is x to the 3rd. We did that a moment ago. The square root of x, since I don't know what x is, I'm just going to leave that under the radical as the square root of x, just like that. All right, so our next few examples are just going to have this, and then we got one more little thing to mop up, and then we're gonna have plenty of time. We're gonna do the next section. The next section is super short, and it has no new material in it. Okay, so that'll be good because I don't want you to leave here too exhausted today. All right, exercise 15. Go ahead and simplify the square root of y to the 15th power. All right, what's the next even number below 15? Okay, so we break this apart into y to the 14th times y. Again, as after you've done a bunch of these and you become proficient, if you do not need to write this next step, I totally understand. Okay, but this is the product rule of radical step. This is the whole point of why it's in this section. And so the square root of y to the 14th is y to the 7th. And then since I don't know what y is, I just leave the other one square root of y. Now, exercise 16, I'm given just because I don't want you to conflate two things. I know that x to the 25th, it looks like you just want to take the square root of that exponent and say this is going to be x to the 5th. But remember, we don't multiply our exponents, we add them. So you got to do the same thing here. You got to go to the next even number below and then simplify. So give that one a try, please. Exercise 16. All right, so while we listen to Professor Dreyer's theory, we're going to go ahead and do this problem right here. So the square root of x to the 25th is, what's the next even number right below? Okay, 24. So we're going to just pull one of those x's out. So now the product rule of radicals says this is the square root of x to the 24th times the square root of x. I can give them each their own radical. And then last but not least, the square root of x to the 24th is x to the 12th, and then times the square root of x. All right, our last problem involving the product rule of radicals here just has both. So notice you've got a number that you're going to have to break apart. You have to find a value that was on the perfect squares list, and then you have an exponent. Okay, so you're doing both things just kind of combined into one problem. Give it a try, and we'll see how you do. Just a minute. And let's see how you did on this. And if you have any questions about when we combine these, and then we'll wrap up this section here. So all you need to do on this problem right here is first the 18. What's the factor on the perfect square list that divides evenly into 18? 9, okay? It's 9 times 2. And then x to the 21st, since that's an odd exponent, I'm going to just pull one of those x's out. So I've got x to the 20th times x. At this point, you can take the square root of the stuff that you can. You can leave the other stuff alone. So I'm just going to write this step out. You don't have to write this step out if this is becoming apparent to you. What I'm going to do under the first radical is I'm going to put the stuff that I'm going to be able to take the square root of, meaning the 9 and the x to the 20th. And the second radical, I'm going to put the stuff that is just going to stay the way it is. So the 2 and the x. If you didn't write it like that, that's fine. Okay, I understand. There's different ways to get to the same answer, but here's what the answer looks like. The square root of 9 is 3. The square root of x to the 20th is x to the 10th. No more radical for those. We did the operation. The 2 and the x, we can't do anything with, so it stays under the radical. So there's going to be 3 or 4 problems in your homework. I got 1 or 2 of those on the test that you're going to take, in addition to some of the other ones, just as we practice the product rule of radicals. All right, one more thing that gets thrown into this section, because there's really not a better place to put it, that I've gotta tell you. The reason I'm letting you know this is the first day of college algebra, whatever instructor you have, if you have me, we talk about this the first day, the Pythagorean theorem, because the Pythagorean theorem allows us to do something fun in college algebra. We're going to be able to use the Pythagorean theorem to figure out the distance between any 2 points on the Cartesian plane. We also use the Pythagorean theorem to figure out an equation for circles. So there's lots of fun in this. But for now, I just need to introduce you to what the Pythagorean theorem is. What it relates to is what's called a right triangle. So a right triangle, it means a triangle that has a 90-degree angle on it. A 90-degree angle is kind of like the wall and the floor, hopefully at 90 degrees. So traditionally, the letters used on my right triangle are these. We use an A and a B for these 2 sides that surround the 90-degree angle. And then we use a C for this longer side on the other side. In case you're curious, the A and the B, these 2 sides are called the legs of my triangle. And then the side C, I don't know who made this word up, some Greek person probably, but it's called the hypotenuse. And so here's the relationship. Now, the reason Pythagoras gets his name associated with this is he's the one that actually mathematically proved it. The Pythagorean theorem had been around a long time before Pythagoras. There's writings of the Babylonians and some other empires even before them. The Egyptians used a lot. Egyptians were really fantastic astronomers, so they knew it. They could numerically use it, but Pythagoras was the person that proved it. But here is the relationship. The relationship is this. If you take the first leg, A, and you square it, and then you add that to the second leg, and you square that, then what that's equal to is the hypotenuse squared. So this interesting thing always to me about the Pythagorean theorem, you don't have to write this part down. This is just me vamping here for a second. Back in the day, they did not have the notation we have for maths, so they thought in terms of geometry. And so if this side was A and this side was B and this side was C, the way they would have explained this, they would have said if we draw a square of length A, right? So this square, the area of the square would be A squared. And then we draw a square here, and the square is, the sides are B, so that would be, the area would be B squared. Then these 2 areas, when you add them up, is always going to be precisely the area of the square that you would draw on the other side. And so that is C squared. So that, to me, it's just interesting when you look at it pictorially like that. And that's how Pythagoras proved it. He used angles and all sorts of fun things to do that. In fact, again, you may or may not be interested. So somebody made a proposal a long time later and said, hey, can I do that for any number? So if I have A to the n plus b to the n. Is there an answer that's c to the nth power? And that was one of math's famous unsolved problems for a long time. And then the proof that this cannot happen is like 300 pages long, and none of us can read it. So anyway, all that to say, sorry, sometimes math I find interesting. So here we go. A squared plus b squared is c squared. We're just going to apply this, and we're going to use it. And the reason it's here is because we're going to be able to apply the product rule of radicals. So here's my example. Then I've got one for you, and then we are done with this section right here. So what we're going to do in example 7 is we're going to find the unknown side. So I've got 5 and 8. Those are my legs. Those are the sides that are around the right angle. And then I don't know the hypotenuse. So it's basically just a plug and chug problem here. So here we go. My first leg is 5. So we've got 5 squared. Plus the second leg is 8. So I've got 8 squared. Then on the other side, my hypotenuse is c. I don't know that, so it's c squared. So we use our calculators a little bit on this problem. So 5 squared is 25. 8 squared is 64. 25 plus 64, that is 89. Now, answer me this question. If c times c is 89, how would I get the c by itself? What would I do to both sides of this equation, do you think? Thank you very much. That's perfectly said. We're going to take the square root of both sides. That's why this is in this section. And so the square root of c squared is c. The square root of 89 is that. And then the question is, can I simplify this anymore? And so we would just go through the perfect square list. Is there a number on the perfect square list that divides into 89? And the answer to that is no. You just take your calculator, go down the list. 89 is a prime number. There's nothing. So this one here is done. But I'm just going to make a little note here that at this point, you simplify if possible, like we did on the previous page. So your problem, this last one, exercise 18, you will end up with a radical that can be simplified. Just a heads up on that. Also notice the missing value is one of the legs, not the hypotenuse. So make sure you plug and chug in the right places. So I'm going to give you a minute or two to look at that. Come up with a thought. All right, so just gonna give this a try, and then we'll be done with this section. So the first leg is 6, so 6 squared, plus the second leg is b, so that is b squared. My b's and my 6's look similar. Sorry about that. And then on the other side, I've got the hypotenuse is 12, so that's 12 squared. 6 squared is 36. 12 squared is 144. Your calculator can tell you that pretty well. I'm going to subtract the 36 from both sides to solve this. And so we get that b squared is equal to 108. Just like you told me on the last problem, I'm now going to take the square root of both sides. And so square root of b squared is b, and then the square root of 108. So then the question is there a factor on my perfect square list, if you need to flip your page to see it, that goes into 108? Anybody get that far? All right, well, I'll give you a little help. 108 is 36 times 3. Okay, just going down the list, figuring out what that factor is. Okay, I have no tricks in my up my sleeve here to figure that out. I just use a calculator and just figure it out. And so then B is going to be the square root of 36 is 6, and then the square root of 3. And there is my simplified answer for what that missing leg is.